Well, it's cold out. Apparently, it's so cold that we couldn't meet together today. So I wanted to go ahead and make a recording of just some feedback on worksheet number 3, feedback that the other 2 sections would have gotten. I'm going to go ahead and release this to the entire class tomorrow, if you're listening to today on Monday, the 15th. That way everyone can see this and have the feedback in a recorded form on this worksheet. So worksheet number 3, as hopefully you know at this point in time, you were asked to essentially map out glycolysis and the malate aspartate shuttle and lactate fermentation, and also the beginnings of gluconeogenesis on this worksheet. And then of course you're to upload that into Canvas. Now let me say this: if you haven't done any of the instructions in the worksheet, I would strongly encourage you to go ahead and pause this and do that. All right, for your own benefit, it really is a powerful learning tool to go ahead and map out these pathways. In fact, the reason that I do these metabolic puzzles, okay, is because I've noticed that students who take the effort to make a metabolic map of all the metabolic pathways that we talk about in this class tend to do better in the course than those who don't take that responsibility upon themselves. And so I wanted to go ahead and give you the opportunity to gain credit for doing that and ask that you do that. Right now, the assignment in worksheet number 3 is the first of 5 assignments that we'll actually do in terms of mapping out all the metabolic pathways that we're going to go over in this class. And there's going to be a total of what I call 8 blocks of pathways by the time we put all this together. Of course, that will be towards the end of the semester. So you'll want to go ahead and keep the things that you've done today, because we're going to do them again and use them again, okay? And so let's go ahead and look at this. Of course, when you look at the blank sheet, and when you looked at the blank sheets for these metabolic maps and these blocks 2, 3, and 4, which is what we're working on today, you saw that there were partial pathways put in there, and of course you were responsible for putting the whole pathway. Okay, so what you are of course looking at here would be glycolysis. I'm using the abbreviated forms of the metabolites within glycolysis. On the exam, I would give you the abbreviated form. I would also give you the full name. So I certainly wouldn't want you to memorize those things, but I would want you and expect you to be able to understand glycolysis in the context of the cell, right? In particular, one of the things that we have spent some time thinking about in regards to glycolysis and even gluconeogenesis is this 6th reaction that would be shown right here, catalyzed by the enzyme GAPDH, or glyceraldehyde 3-phosphate dehydrogenase. That enzyme, sorry, just got a text if you heard that ding, but anyway, that enzyme is going to catalyze the 6th step in the pathway, as I've already mentioned, but it also requires NAD+ if the pathway is running towards glycolysis and the production of pyruvate. And if it's going in the direction of to produce glucose, it needs NADH. Okay, so there has to be some way to supply those metabolites to the cytosol when flux through either one of those pathways is increasing. Right. So what I'm talking about here is, of course, NAD+ is converted to NADH. Okay, and what we see here is this: that NADH can be quickly recycled back to the NAD+ by this reaction down here that will be catalyzed by the enzyme LDH. We didn't need to list enzymes on this, but that would be the enzyme that does that. It will do that in both aerobic and anaerobic conditions, though we talked about it more in regards to anaerobic conditions because it's a very prevalent reaction if a cell like a skeletal muscle were to go anaerobic. Okay. Now, this is where we then have the opportunity, though, to start to see how this pathway can connect to some of those other pathways that we talked about, in particular the malate aspartate shuttle. Right. So let me go ahead and do this. We've got this NADH that I'm going to go ahead and say is going to come all the way down here onto our 3rd block. Okay, so this would be block 3 down here. Notice that we have the cytosol here, we have the intermembrane space here, and we have the matrix here, and of course these lines represent the inner membrane and the outer membrane of the mitochondria, with the inner membrane having these 4 blocks in it, and then the outer membrane having these big holes in it that would represent those porins. Okay, so that NADH then can come down here, and it can actually get converted back to the NAD+, and then that NAD+, of course, can be recycled all the way back up to here. Okay, all right, so in any case, how does that happen? Well, that's what we're looking at here would be the conversion of oxoacetate to malate. Okay, it can be reduced with the electrons from NADH to malate, and then that starts the malate aspartate shuttle, and it's going to go in this counterclockwise direction. Okay, and that malate can move through one of these antiporters into the matrix of the mitochondria, and then I wanted you to go ahead and span that across into block 4. Okay, and have this malate be essentially what was produced in the cytosol, and then that malate can be converted right back to oxoacetate using NAD+ in the matrix of the mitochondria, making NADH, and then that NADH is going to go on and do some pretty cool stuff. Okay, and then of course we can get that oxoacetate back, and that's essentially what's being shown here. Okay, and I won't spend a lot of time belaboring the alpha-ketoglutarate and aspartate and the glutamate's role, but they would play a role in this and what we call transamination reactions. Okay, and that's the malate aspartate shuttle running in the counterclockwise direction. Okay. Right, now, the other thing here, and this is the last thing I want to mention with this, is that pyruvate, right, can and will go into the matrix of the mitochondria. And the fate of pyruvate in the mitochondria, there's multiple fates of it. We have yet to really discuss those, okay, especially when that pyruvate is generated from a carbohydrate like glucose. We are going to talk about how pyruvate can be converted to acetyl-CoA, that can go through the citric acid cycle, and that will be a later metabolic map that we'll make on block 4, actually. Okay, and that's why I want you to keep these things, right? However, we can say this, right, and this is in regards to what we talked about in our first unit of the class, and that is that we know this can happen. Okay, for instance, amino acids can be converted to pyruvate. Okay, or we could go back this direction. Lactate can be converted to pyruvate. Either one of those can happen. Okay, and in those cases, if you have this increase in pyruvate from lactate or amino acids in the liver, what's more than likely happening is that flux through gluconeogenesis is starting to increase. Okay, and that pyruvate can then move into the matrix of the mitochondria, and this first step here would be catalyzed. This one right here would be catalyzed by the enzyme pyruvate carboxylase, essentially the addition of a carbon to pyruvate to make oxoacetate. Okay, and that would then start the pathway of gluconeogenesis. Now, oxoacetate, if that's happening, right, understand that this is not pyruvate made from glycolysis, so you don't make pyruvate from glucose to then take pyruvate to make glucose. That doesn't happen in the liver, okay? There are going to be a depression of the flux through glycolysis if there's an increase in the production of glucose through gluconeogenesis. In other words, if flux through gluconeogenesis goes up, flux through glycolysis will go down, and that's what we'll talk about in our next unit of the class. Right, but nonetheless, we have these other routes where pyruvate can be converted to oxoacetate to make in gluconeogenesis, and then what will happen if that happens? If this goes up, this will go in this direction, and the malate aspartate shuttle will start to run in the clockwise direction. Okay, and then this NAD+ will be made to NADH, and this NADH will then be taken up and used. Okay, essentially in not glycolysis any longer, but remember, this is going to be going in that direction now. Okay, now I didn't ask you in this worksheet. Some of you are like, did I need to put all that in the worksheet? No, the worksheet didn't ask you to do that, because then it would overcomplicate, quite honestly, the worksheet. So I didn't really want to ask you to do that. I'm just showing you for your own benefit what would happen here. Now, something to consider is this oxoacetate, when produced here, can be converted by pepCK to PEP, and that would then start gluconeogenesis in the cytosol. Okay, so keep all these things in mind as you're making these metabolic maps. Certainly you can add to your metabolic map gluconeogenesis and show the pathways here. I didn't ask you to do it, so it doesn't have to be on the one that you turn in, but certainly it's going to be helpful for you to understand that when we have amino acids, or when we have lactate or some other source of pyruvate that can make oxaloacetate, the malate aspartate shuttle will run in the opposite direction than if it were to be gaining NADH from, let's say, glycolysis. Okay, so let's go ahead and stop there. I hope that this recording has made sense to you and has helped you out. We will get back together as a class for the Q&A session tomorrow, Tuesday, the 16th. I will be running it from 2 to 2:50. So bring your questions. If I don't see you there, I'm going to make a recording of that. All right. But if I don't see you there, then I'll see you the following week in a face-to-face session. Okay? All right. Take care, everyone.